I'll maybe just we'll maybe just try to understand what's the concept of D-Wave, because first, just playing with the example seems to be not that straightforward, as I must have quota. I don't want to create another account, but it says I have 1 minute. So expired. Get more time. Oh, come on. Good. So let's get, so we try to go through the demos, and kind of I got I try to go through the demos, and I got a sense of what it means, right? So just to recap, basically it's about energy functions. So you prepare an energy function that encodes your logic in a probabilistic way, in the sense that the lowest values of that equation, so the lowest energy levels, are the ones with the highest probability. That's what the example was trying to walk us through. But how that takes us to the solution, was not clear to me. So I'm going to try to figure that out today, and then we'll move on to something else, because I think that's going to be first enough resources. The demos, we've done the demos. Develop tools, learning in docs. Good. Learn how to program the quantum computer. Okay. With interactive examples, that might be. Okay, the documentation and the system documentation. Let's start with the interactive examples. That can be maybe the best way to start building up some more intuition around this topic. So good. Using interactive Jupyter notebooks, you can access interactive examples that will help you learn to formulate problems for the DWave system to solve. So it seems like all you have to do is to formulate a problem and then let the computer solve it, right? Which is, it feels a bit limiting from an intuitive perspective, because I would prefer to know that I have a mechanism to move information around, so then I can come with weird ideas and stuff like that. And this is more like, okay, so you've got a problem, please translate it into a sort of a way or a format that our DWave computer can solve it, and then let us solve it, which is good for really purpose-specific, tasks. But it might not be good enough for a broader usage, so to say. So what do we have here? Explorer view, notebooks, difficulty level. Well, we'll start. Okay, so we have intermediate, data solutions, factoring. We went through factoring, and we can do factoring. Maybe anneal schedule, reverse anneal, structural imbalance. I mean, those are the same things like we saw in the demos. Okay, let's start with the factoring one then. Explains the QPU programming model used for factoring and how to implement that using DWave. So by the end of the notebook, you will have seen how to convert a problem into a binary quadratic model for submission to the DWave system. Okay, let's see. Let's open the notebook. Hopefully I don't have to install anything. And it's just an online Jupyter notebook, yes. Okay, that's a lot of text. Okay. Let's start from scratch. So in the factoring demo, you saw that the DWave system factored an integer by running a multiplication circuit in reverse. No, we didn't see that, but yeah, because we couldn't. The notebook demonstrates how you can solve a constraint satisfaction problem, CSP, on a quantum computer with an example of factoring. Okay, so basically it's going to take us through 5 different steps. Factoring as a CSP, formulating the problem for the DWave, an example, further information. So the complexity class for classical integer, I'm just gonna quickly read through that. I mean, for quantum computing, polynomial time. Yeah, that's the thing, So that's the the DWave system does not run this algorithm because Shor's algorithm, which is a famous quantum textbook algorithm, is it's done with quantum gates and other stuff. I think it's a different type of way of implementing a quantum computer, so to say. This notebook solves factoring on a D-Wave quantum computer by formulating it as a constraint satisfaction problem. It requires that all problems variables be assigned values. For factoring, the problem's constraints are that the two variables representing factors A and B be assigned only natural numbers and that their multiplication be equal to the factored number P. Yeah, but I thought it was about prime factors. Okay, whatever. For example, the map coloring problem is to color regions in the maps, whatever, yeah. So this is all blah, blah. Formulating the problem for a D-Wave system. So how can we formulate the factoring problem in a way that a D-Wave quantum computer can understand? D-Wave systems solve binary quadratic models, the Ising model traditionally used in statistical mechanics and its computer science equivalent. The quadratic unconstrained binary optimization problem, QUBO, given n variables, where each variable can have binary values, the system finds assignments of values that minimize. Okay, yeah, so we saw that in the table as well. So basically, yeah, that minimize that, and that's why, okay. And that's why, and they talked about minimizing, so the values with the lowest energy level will be the most probable ones. So here they walk us through how can we formulate the factoring problem. Like the first sentence, feel comfortable skipping this subsection if you prefer to move on to what we'll be coding. I mean, I think that's probably what we're going to do, because I'm not interested really in the deep math behind those things, unless then, I really don't understand something and I want to make sure that it makes sense. But quickly, basically, they explain you how to formulate that. So yeah, equation, blah, 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 formulation B. So formulation B, an alternative is to express the constraints of the problem with Boolean logic. This technique is very versatile. Modern computing is built on Boolean gates. Yeah, the scope of addressable problems is immense. Our implementation below follows these steps. So you express P as A times B, convert to a BQM, program the quantum computer with a BQM's coefficients. The section illustrates the steps of simulation B. For some problem, a circuit with two switches that turns on a light. Yeah, I thought that would be clickable, but it's not. Express the CSP with Boolean logic. So we can express the problem of how to turn on the light as a CSP with a single constraint for a light L. I mean, it just feels a bit tedious to go through all that. And maybe it's me and I'm again lazy. But I think I'm just might skip the example. Must be logic, and logic expresses constraint as conjunction these and these. Unlike real world, which has thousands of constraints that have simultaneously don't yeah, that's the example of that, right? So basically, sure. I mean, only if both are on, then the bulb turns on. Yeah, we know that's the end. Yeah. Ocean's D-Wave binary CSP tool provides factories for useful constraints such as logic gates. Okay. Run the cell below by pressing the run button with your mouse. In the cell to create a CSP with a constraint presenting an AND gate. The run, this, I guess this is this. Out true, so the output is true. So what is Okay, so that's already code, and then basically there's already a function or subroutine called AND-gate to satisfy those constraints. Okay, so and then this is the check. So, and I'm guessing that if I were to change that to 0 and I would do the same, then it would just say false. Exactly. Exactly. So, yeah, same here. So I mean, as long as I'm guessing, I guess that's what it is. So if you put all 1, then it just runs. Yay, good. Still, that's just okay. A constraint. Convert to a BQM. The quantum computer solves binary quadratic models. Let's express our light circuit. I can't pronounce this word. CSB as a BQM. An advantage of formulation B is that BQMs are known for logic gates. You can find BQMs for gates in the DWave system documentation and see examples here. Let's see what's in there. In a second, more than one BQM can represent our AND gate. It's just polynomial of binary variables with only linear and quadratic terms. Ocean tools can do that, can do the math for you, but here's the first, here let's first write our BQM for the AND gate. So this. To see that this BQM represents the AND gate, you can set its variables to the values of the AND truth. Yeah. Okay, so basically this is just turning in the Boolean logic into like sort of a mathematical representation that takes basically both inputs and expected output of the Boolean operator and then just basically represents that, like it's built as an equation that then gives you the same type of output. Okay, so I guess, and that code is probably gonna just print. Okay, so it's iterating over the different values of x1, x2, and x3 being either 0 or 1. Yeah, and then printing that stuff. And here you have, so that is the wait a second, that is not the n though. Oh, again, so only the values that are 0 are the ones that we care about. Exactly. The values that are 1 are not, because it's that's I mean, it's just the way this is defined, right? Good. So convert, solve by minimization. What does this do? Okay. Okay. So that gives you already the BQM. Basically, that's the coefficients. Not really, but linear. So that's linear and that's quadratic. Yeah, it doesn't. Now let's just to convert in the BQM the code coefficients, the inputs used to parent the DWave system. As noted, more than one BQM can represent our AND gate. So the BQM generated here does not have to match. Okay, that's what I was checking, because it just didn't match this one, but it does the same. Lastly, we solved the problem by finding variable values. Good. So we solved the problem by finding variable values that produce the lowest BQM values. For real-world problems with large numbers of variables and constraints, minimizing the BQM is hard. This is where a quantum computer comes in handy. Let's see that. The next section, which solves the factoring problem, uses the DWave system. For this trivial example, instead of using the DWave system as a sampler, we will use one of Ocean's software test samplers. Yeah, and that's probably what you should use for the demos as well, and not just a real quota. Ocean's Diamond. What is the Ocean's Diamond? Ocean's Diamond. It's an API. Okay. Ocean's Diamond provides one that simply returns the BQM's value for every possible assignment of variable values. The next cell prints BQM's values energy in ascending order. Okay. Yeah. So I mean, basically those are the ones we're looking for. In that case, they solve the constraints of the problem. Yeah. Factoring in a quantum computer. Selection solves a factoring problem as a CSP, blah, blah. Express factoring as a multiplication circuit. We again start by expressing the problem with Boolean logic gates, in this case, a multiplication circuit. Okay. So basically, that's what they did in the demo, right? So the target is factor 21. So basically represent that as a multiplication circuit. Binary multipliers are made with logic gates like the AND gate. We used both, understanding the factoring example, and its application to solving CSP does not require understanding of binary multiplication. If you do want to know more, say further. Okay, whatever. Set an integer to factor a binary representation of P. Formats for 6-bit binary. Yeah, just this. Yeah, so that's 21 in binary. Yeah, it just seems unnecessarily complicated in terms of, from an intuition perspective. I don't know. We'll see. We'll see. This, run the cell to create a CSP for a 3-bit. Okay, so multiplication circuit. So okay, so that already comes in as a given. Let's run that. Convert that. Okay, so you've got, so basically what we have now is, we'll print here is the frozen set, blah, 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 blah. So that's the multiplication circuit in binary, and now we're converting it into a BQM. We express the multiplication circuit as a BQM that provides the coefficients used to program the problem on a DWave system. Okay. It's just, I'm gonna go through that. It doesn't seem like, okay. Blah. Okay. So how is that? Yeah, so this is what? This is a number, like, what? I got lost for a second. So gap circuit 3, what's the 3 for? It's the number of bits, or the number of parameters. Convert to a BQM. And as in the factoring demo, the DWave system factors are integer by running multiplications in reverse. Below we fix the variables on the multiplication. Okay, so those are the input variables here. Oh, I see. Okay, it just, the layout confused me a bit. So those are the 6 and just the fact that it's on that side. So those are the 6 output values, and here we have all our input variables. So basically this means that so you can use that exactly. So we put in here the outcome, and then we'll see what happens here. So we'll put here the outcome we want, which is 21, and then we'll see how that in reverse turns into its factors. That's what it is. Okay. Creates these variables, converts p from decimal to binary. No, the other way around. This is the outcome. I see now. This is the outcome. So we start here, and then we work our way back. And this is one, and this is another one. So actually, that's smartly laid out so that we see a difference, because this is one factor and this is another factor. Good. Yeah. So what does it do? It fixes the product variables. Confirm that a p variable has been removed from the BQM. Okay. So you convert the p for this from decimal to binary. That's good. Then we don't know what this is. So what does this do? Below we fix the variables for the multiplication circuit's BQM to the binary digits of the factored number p. This modifies the BQM by removing the known variables and updating neighboring values accordingly. Removing the known variables and updating. Let's just run that. Submit to the quantum computer. Lastly, we'll solve the BQM by finding variable. Lastly, we solve the BQM by finding variable assignments that produce its lowest values. Here we use a DWave system, setting up a solver. So yeah, the solver, that's what we use to solve that, whether it's the quantum computer or whatever tester. Use the DWave system as a sampler. QPU true. I guess I gotta run that. So I'm running that. API token. Running that. Mapping between the graph of our problem. Graph no symbol. Minor embedding. A problem can be minor embedded into the QPU in a variety of ways, and this affects solution quality and performance. Ocean software provides tools suited for different types of problems. For example, DWave system composite. Okay, that doesn't. That's. I think I'm being too much. I'm spending too much time in the details, but I really want to understand just a little bit of the code. Variables. Let's run that. Solves the problem. So when okay, that's maybe an interesting part. So when the DWave quantum computer solves a problem, it uses quantum phenomena such as superposition and tunneling to explore all possible solutions simultaneously and find a set of the best ones. Because the sample solution is probabilistic, return solutions may differ between runs. Typically, when submitting a problem to the system, we ask for many samples, not just one. This way, we see multiple best answers and reduce the probability of setting on a suboptimal answer. In the code below, numerics should provide enough samples to make it likely a valid answer is among them. 50. Okay. So it's 50. Okay. So if we run that, what happens? And here it is again. Solve a failure error. Is it again my quota or what? Yeah, of course. Come on. Come on. Yeah, whatever, it's just binary multiplication. Okay, so this is more the math behind that, and then samples and solutions, minor embedding. Not interesting. So, but still, it's not clear how does the quantum computer do that. So they say using quantum phenomena like superposition, and tunneling, right? But it's still leave